We're in section 5.5, L'Hopital's rule. Remember that at the beginning of this course, we learned limits. And we learned that the derivative was a special kind of limit, and then we learned all about derivatives. Now we're kind of going full circle, because we're going to use the derivative as a technique to find certain limits that we weren't able to find before. So quickly, remember the ways that we used to find limits. We would use algebra to simplify, we would factor, multiply by the conjugate, common denominator with fractions. The case when x is approaching infinity, we divide by the lower degree term for the polynomials. There was a squeeze theorem. But what about a problem like this? That doesn't really work. None of those techniques work for this problem. So we have to come up with something else. Well, it turns out we do have something else called L'Hopital's rule, which, by the way, was not proved by L'Hopital. It was proved by one of the Bernoulli brothers. L'Hopital sort of bought the rights to the proof. Anyway, suppose that we have a limit that gives an indeterminate form 0 over 0 or infinity over infinity. Then I really should have let you fill this in, but it turns out the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. So you just take the derivative of the top, take the derivative of the bottom, and try again. Now, a quick little proof as to why this works. This is an oversimplification. This is similar to what the book has. This is an oversimplification. I'll do it a little differently from the way the book does it, but recall that if f of 0, or no, I should say rather, if f of a equals g of a equals 0, then, so remember what's going to happen. Remember the definition of the derivative? Remember the point definition of the derivative? We have that f prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. And of course, the analogous thing is true for g prime of a, right? Right? So we have that. Actually, you know what? Let me go ahead and move this proof. Let me see if I can not get that line there. There we go. Move this over here just because I want to stick this over here. Okay. Right, so we have this, okay? So the limit as x approaches a of f of x over g of x equals, well, hold on a second. Let's see what happens with this definition of the derivative, right? I guess we could really just say, you know, let's see, what am I guess what we could do is we could just tack on this. Watch, f of x minus f of a and g of x minus g of a. I guess we could do that, right? Because they both equal 0. Right? So we're just adding 0. That's not really doing anything, right? Okay. And, well, I guess another thing we could do is say, all right, well then, this is going to get a little nasty because it's going to be a repeated fraction. But I guess what we could do is we could say, well, I guess we have this. Right, I'm just including the over x minus a part. Right? And I guess even further, what I could do is say, well, you know, assuming these limits both exist, which they do, because the derivatives exist, as we'll see in a sec, I could split the limit up over the quotient. And this is really the same thing as the limit as x approaches a of f prime of x over g prime of x. Right? We just have the definition of the derivative. So there you have it. Now, this is, again, a simplified proof. It's not quite this simple. The book mentions you really need a generalized version of the mean value theorem, but this is a basic proof. You can do something similar with infinity over infinity. So anyway, this is not the quotient rule. This is something much easier, right? If we were to solve this limit, right, find the limit as x approaches infinity of ln of x over x, what we do is we just take the limit as x approaches, well, not a, infinity. And by the way, this does work for infinity too. Let's see what we get. Oops, what is my problem? So first off, we know that we have an indeterminate form, right? Infinity over infinity. So it's no good. Okay. So I'm going to write an equals and I'm going to write an LH. I keep the limit as x approaches infinity, and I write just the derivative over the derivative, right? The derivative of ln of x is 1 over x. The derivative of x is just 1. So I get that. And of course, we can simplify this very nicely, and I hope we see that we get an answer of 0. Okay? So this limit does in fact equal 0. X grows quicker than ln of x. But that's how we did it. Okay? Let's do a couple more examples. This one looks a little more complicated. And if you ever take Calc 2, you might see this guy rear its ugly head again. But just note that we do, in fact, have 0 over 0, right? Because e to the 0 equals 1. And then we have minus 1 minus x. Right? So just make a note of that. Okay? So anyway, because we have 0 over 0, we can use L'Hopital's rule. Take the derivative of the first. E to the x stays the same. Minus 1 goes away. Minus x turns into minus 1. And we have this. Well, what happens now? Well, if you plug in 0, you get 0 over 0. Okay, well, I guess we have to keep going. And then we're going to use L'Hopital's rule again, right? Nothing says we can't use it more than once. And we get e to the x over 2. And at this point, we get 1/2. So that's our limit. Okay. Number 2. For number 2, we have limit as x approaches infinity of ln of x. And this is an interesting one, right? Which grows slower? They're both kind of slow-growing functions. Well, you might notice they do both equal infinity if you were to plug in big numbers of x, right? So we're going to use L'Hopital's rule. Derivative of the top over the derivative of the bottom. This is a little icky right here. Now, at this point, if you try to take the limit, you're going to get 0 over 0. Not very helpful. But we can simplify this fraction. Remember, dividing by a fraction means multiplying by a reciprocal. So you wind up getting 2 root x over x. And at this point, you can do some cancellation. Right? And so really we're getting just the limit as x approaches infinity of 2 over root x, and this equals 0. Right? So it turns out root x actually does grow quicker than ln of x. All right, now pause the video. Try to do example 3. Okay? If you got an answer of maybe 3/8 or negative 3/8, you are wrong. Because we do not use L'Hopital's rule in this situation. The limit does not give us an indeterminate form. It gives us, I believe it's negative 1 over 11. So that's your answer. So just make sure that you have an indeterminate form before using L'Hopital's rule. Otherwise, you're not allowed to use it. All right. Now, the thing with L'Hopital's rule is it works only if it's a fraction, right? Like if it's 0 over 0, infinity over infinity. So if we have an example like example 4, we're in a bit of a pickle here because we don't have a fraction, right? We have an indeterminate form, as it turns out. I'll show you in a sec, right? We have limit as x approaches 0 of x times ln of x. Remember that as x approaches 0, this, by the way, should be from the right. I should be doing that right there. That should be a plus right there, because ln of x is not defined for 0 or negatives. But anyway, remember that as x approaches 0 from the right, ln of x approaches negative infinity. So our indeterminate form is actually 0 times negative infinity. It's kind of weird. So we can't use L'Hopital's rule, because that is not 0 over 0 or infinity over infinity. However, we can use a trick. Very clever trick. Instead of writing it as x times ln of x, we can write it as ln of x divided by 1 over x. You see what we did right there? We, instead of multiplying by x, did the much more complicated thing and divided by 1 over x. And while that would not be a good idea most of the time, in this case, it actually works out nicely because we have negative infinity over infinity. And that is an indeterminate form we can work with. And so that is something we can use L'Hopital's rule on. And so we're going to get 1 over x, and this is over negative 1 over x squared. Again, if you did it right, you took the limit right there, you're getting another sort of infinity over infinity situation. But remember, we can simplify, and we get negative, we should be taking the limit. Is what, negative x squared over x. Stuff cancels, and we're left with 0. Okay, so it turns out the answer is 0. But we had to do that extra step. Before just doing L'Hopital's rule, we had to divide by 1 over instead of multiplying. Right, try this one. Same sort of thing. Try pausing the video and doing this one. Right, we have the limit as x approaches infinity of x tangent of 1 over x. And that is going to give us infinity times, turns out it's 0. Tangent of 0 is 0. There. And now you might notice that we do in fact have 0 over 0, so we do get to use L'Hopital's rule. And so we're going to get secant squared of 1 over x times the derivative of 1 over x divided by the derivative of, well, 1 over x. And oh my goodness, isn't that nice? Right? Everything cancels. And we're left with the limit as x approaches infinity of secant squared of 1 over x. Now, that's going to be secant squared of 0, which is 1. So we get 1. Okay. And I think we will stop here.